All right. So, kind of wrapping up chapter 14. There's a whole lot more we can do with chapter 14, but we're running a little short of time. So, let's consider a general case of we've got a pipe, and the pipe comes up here like that and narrows as it goes. So we got A1 here, we got A2 up here. And so this is going to be at some height right here. And this some height like Y1. This end of it is going to be at some height Y2. Obviously, we got V1, we got V2. Okay. And so we want to describe what's happening here. Okay. Well, clearly, if you look at it, we've got some potential and kinetic energy at one end. We got some potential and kinetic energy at the other end. So let's look at this as an energy thing. It's increased in potential energy, and if I narrow the pipe, it's also increased in kinetic energy. So what that means is that we've got the initial kinetic plus the initial potential. We got to do work on it in order to get the final kinetic plus the final potential. Okay. So thinking about this again, comes up here, we got some A1, we got some A2, we got some V1, some V2. This is going to be at some Y1, that's going to be at some Y2. So the initial kinetic is 1/2 mv1 squared. The final kinetic is 1/2 mv2 squared. The initial potential is going to be mgy1. The final potential is going to be mgy2. Okay, now we got to do work. Now work, remember, is going to be force times area. Not sorry, force times distance. Okay, well, you look at that and say, well, okay, so force in fluids would be pressure times area. So we would have some pressure down here pushing on it. So that's pushing P1, A1, X1. So it goes some distance X1 in a certain amount of time. Well, it comes out some X2 up here, okay, and over some area 2. But if there's any pressure up here, that's pushing back. So that's going to be negative or minus P2, A2, X2. Now, we know A1X1 has to equal A2X2. Volume in equals volume out, assuming this is incompressible. So if I divide everything in this equation by volume, those cancel. And then mass over volume is density. So I have 1/2 rho V1 squared plus rho G Y1 plus P1 minus P2 equals 1/2 rho V2 squared plus rho G Y2. Well, if I move that to the other side of the equation, I've got P1 plus 1/2 rho V1 squared plus rho gy1 equals P2 plus 1/2 rho V2 squared plus rho gy2. Basically, what I found is the pressure plus 1/2 rho V squared plus rho gy is a constant. Okay, because this is all ones over here, that's all twos over there. So wherever you are in this pipe, then this relationship holds. Okay, so we call that the Bernoulli equation. So that is the Bernoulli equation, and that turns out to be really fundamental to understanding fluid dynamics.